Hello everyone, this is Yu Han from the Civil Engineering Department in National Taiwan University. It's my great honor to present our latest solution for solar photovoltaic potential analysis based on modern geospatial information technique. Due to the depletion of fossil fuel and the carbon-induced climate changes in the foreseeable future, most of the countries in the world have set up targets on replacing high carbon emission energies with more clean and renewable ones. According to the Renewables 2020 Global Status Report, solar power, wind power, hydropower, biopower, and ocean power are among the most viable and renewable energies. An 8% growth rate on these renewable energies has been achieved during the past 5 years. Among the different types of renewable energies, the solar photovoltaic energy is considered as one of the most well-adapted resources. It is projected that by 2050, the renewables will make up 50% of the world's total energy, and half of it comes from solar generation. In other words, solar energy is expected to play an essential role in the world's future energy supply. In order to achieve the above-mentioned goal, a great amount of solar power plants has to be constructed everywhere in the world. However, due to its low power production densities, a solar power plant requires a big source of land in order to reach financial balance. Although large solar power plants can be placed in a less populated area where the land cost is low, over 50% of power consumption is actually from the highly populated cities with limited and pricey lands. As a consequence, setting up a large solar power plant to fulfill the local energy demand in urban areas is not a feasible solution. To share the power generation and to improve energy self-sufficiency in urban areas, setting up small solar power systems on buildings becomes a must choice. All residential, commercial, and industrial buildings can provide certain space to install small solar power generation units without incurring extra land cost. Clearly, such an approach can also increase the property use and value. Although solar panels can be installed on rooftops or building facades, rooftop system is the typical choice because it can receive the maximum vertical irradiation and has less impact on the building's appearance. However, the location, the orientation of a solar panel, and its surrounding conditions are key factors affecting the performance of a rooftop solar power system. In an urban area, buildings have different heights and shapes. Such factors not only affect the usable space for solar panels, but also produce various shadowing effects to the surrounding buildings. This downscale model demonstrates how the distribution and 3D geometry of nearby buildings impact the solar energy production on different rooftops across time. Typically, low buildings have higher possibility to be affected by nearby tall buildings. Besides, the facing orientation of non-planar rooftops is also a key factor, causing different power generation rates from these buildings. Due to the complexity of the building geometry in a city, an accurate evaluation on the rooftop solar energy potential becomes a challenging task. To provide a realistic metro-scale evaluation for the solar irradiation potential, our team developed an integrated solution based on modern geospatial information techniques. 3 major components are included in our approach, which are a realistic solar irradiation model, a high-detail 3D terrain and building model, and a geometric analysis module. That together can be used to identify useful space for solar panels, to compute shadowing effect, and to estimate solar irradiations. First, to realize the amount of solar irradiation arriving at each location on the ground, the TMY model produced by the Architecture and Building Research Institute in Taiwan is used. It enables an hourly solar irradiation forecast based on observation from widely distributed ground stations in the country. Using this model, one can compute the solar irradiation intensity and incident angle arriving at each specific location. Additionally, the current model was developed by about 10 years ago. which may not be able to fairly represent the recent and even future weather conditions. To answer this doubt, our team further utilized the remotely sensed images from the Japanese Himalaya satellite to estimate the regional irradiance condition for the recent 10 years. Corresponding data from Guam Weather Station was also considered to calibrate this updated model. We finally produced a solar irradiation map with a 2-kilometer ground resolution for the whole country. It enables a much realistic solar irradiation forecast in this region. As mentioned above, city buildings come with different heights and shapes. A digital 3D model showing a building's geometry is thus required for the analysis. However, establishing a 3D building model could be very expensive and time-consuming, depending on how detailed the model is. This is defined by the level of detail LOD value. The higher the LOD value, the much detailed the building is. These figures shows the building models with different LOD values. In LOD1 model, there's only the height, but not much detail. The roof is assumed flat, which is not realistic. Compared to LD1, LD2 model contains the actual roof shape. It is thus more suitable for the rooftop solar system analysis. In addition to the building model, the terrain relief was also considered in our approach. A high-resolution digital terrain model (DTM) generated from airborne LiDAR was also used together with the LD2 building model to recreate the actual landscape and geometry of a city. This is an example of the city-scale 3D model used in our solution. As illustrated, variation of height and location of building can all be simulated, so further analysis can be performed in a much realistic manner. Finally, with the solar irradiation model and the city building model, a module for extracting all the useful building roof, including their location, height, areas, slope, and aspect angles, is developed. The shading of an area at each hour on each day can also be computed for each roof. With all this information, we can evaluate the receivable solar irradiation and possible energy generation for each individual rooftop solar panel. The same can be done for the buildings in a specific region or for the whole city. Here we demonstrate some results. We apply our technique to 8 districts in Taipei City using LD2 building model. The top figure illustrates the aspect angles of each roof element, and the bottom figure shows the solar irradiation received on each rooftop. Finally, we estimate all the useful roof areas for installing solar panels and predict the maximum energy generation in each district. The values range from 8 gigawatts to 92 gigawatts, which can generally cover the energy demand of the residential household in each district. Most importantly, up to 4% of solar energy reduction is observed due to the shadowing effect. We also did the same for the whole city using a simplified LD1 data. Compared to the result from LD2 data, we can see a obvious difference on the shadowing effect. It gives a strong support that the LD2 building model used in our solution will make a significant contribution in such an analysis. A simulation can also be performed using our approach for identifying the optimal setting of solar panels. The left figures shows the optimal slope and aspect angles for each month in a year to receive the maximum solar irradiation. Based on this information, a solar tracking system can be designed, ensuring that the solar panels can operate in their best capacity all year round. If a solar tracking device is not available, then the fixed 13-degree slope and 172-degree aspect angles should be used in this region. In summary, first, we provide a complete solar photovoltaic potential analysis solution using high-detail 3D building and terrain models, up-to-date meteorological data, and 3D geometric analysis module. It provides not only a visual but also numerical representation of such analysis. Secondly, our solution combines the latest and sophisticated data and provides highly reliable solar potential analysis. Finally, our technique is fully automatic and can thus be applied for a large city scale. Its result can be considered as a scientific evidence to support the solar energy policy, planning, and development for a public or private sector. Lastly, we acknowledge the funding support from MOST in Taiwan. We also appreciate MOI, CWB, and Taipei City government for making the data available. That's all my presentation. Thank you very much for your listening.